children, how are you doing? I hope you are doing good, great, right? I came to see you with a new video to explain you a new lesson, EdXL A level. This is chemistry, right? Okay, now look at your heading 9B, first lesson, reversible reactions and dynamic equilibrium, right? I'll break the lesson into few sections, right? I'm going to talk about irreversible reactions. What is this? What do you mean by that? From the beginning, the day that you have learned chemistry, you have learned sort of equations, chemical equations. You studied to balance them too. And by the way, whenever two reactants are there, it gives one product or two products. But eventually you came to know sometimes what you have produced, what they have produced can come back to their normal initial stage too, right? So these are I have pointed out two examples for you. One is magnesium burned in the air with oxygen gives you magnesium oxide. I have balanced it, done. It cannot be happened, it cannot come back to the initial stage. Just think, this is sort of, this is a pen, but it is covered with aluminium. This aluminium reacts with oxygen in the atmosphere. What will happen? That oxygen reacts with aluminium and makes oxide, a layer, aluminium oxide, and it protects this. It's a layer over it, right? Likewise, this is also a similar example for that, right? What about this one? Neutralization reaction. Sodium chloride with sulfuric acid, a base acid gives you the salt as well as, what was it? Sodium sulfate plus HCl. Yes, we balanced it. 2 sodium atoms, 2 sodium, chlorine, okay, right? Sulfate also 1, 1 here, right? This sort of reactions won't come back to their initial stage. Okay, now see what will happen. Reversible reactions. This is not chemistry, this is English, right? Reversible. Reverse. When it is reverse, what will happen? When you drive a car, you drive forward. At the same time, there's what you call a sort of a traffic jam or something, a sudden incident happens, you have to reverse it. This is also like that. What will happen? Hydrous copper sulfate. Copper sulfate is in solid state. When we add 5 moles of water, it turns to what? Once it was anhydrous, right? We added water, then it turns to hydrous copper sulfate. Okay, let me tell you once again. You have copper sulfate, you added water. Once it was anhydrous, when you added water, it turns to hydrous copper sulfate. Okay, fine. Then what will happen? If you heat it, then it will separate. The water will evaporate. What? Copper sulfate remains as solid and you can find water as liquid. But my dear children, this reaction will happen again and again. You can begins with this and ends with that. Once again it starts or it begins from this side and come back to the initial stage. This will happen again and again. This sort of reactions are known as reversible reactions. Okay, next one. Gaseous ammonia and gaseous hydrochloric. What will happen? You will form solid ammonium chloride. It will be a cloud, just like a white ring. Whenever they reacted, you can identify whether the ammonium chloride is formed by seeing a white ring, a cloud. It's a solid. So my dear children, this reaction is another example to prove that Actually what? To prove this belongs to a reversible reaction. You start with two products and you gain a product, but eventually what you gain come back to the initial stage. Right? To show, to prove that this is an reversible reactions without word. Now you can use words, but without writing words, a chemistry student knows by seeing this symbol, this is a reversible reaction. Right? Okay, let's move on to the next part of this. Deducing whether the reaction is reversible. It's very important for us because every reaction is not reversible, right? So we have to deduce, we have to find it out. So see, I wrote a small summary. It depends whether the reaction is reversible. Depends on what? How carefully we measure the concentrations of what? The reactants, your left hand side, and the products, your right hand side. Example is given here. One is a dilute HCl with aqueous sodium hydroxide. You know the ionization process here. Let me write it for your convenience. Yeah, there, here. You can break this. Hydrogen, cation, chloride, anion, aqueous. I'm sorry I did not, this is here. I wrote dilute here. Don't worry. Then sodium hydroxide, sodium cation, hydroxide anion. Fine. Sodium chloride, also you have to ionize. Fine. H2O is liquid, so you are not going to write it for the moment, right? I will talk about H2O after a few minutes. Right, my dear children, this is, in the classroom I taught you, whenever we are writing a chemical equation, it's like a simple equation. You have to balance either the both sides, I mean the left side and the right hand side. Whatever you do to your right hand side, you should do it to your left hand side too, right? So you can simplify this one. Chloride ion with that chloride ion cancelled. Sodium, sodium, right. What are the remaining portions? What are the remaining ions? H plus, OH minus, H2O. Now forget about these things. What will happen? Whenever you collect these things, you will receive water. These two sides are balanced. Okay? Right. Now I promise you I will talk about water. My dear children, pure water, I hope you can remember the shape of water. This is oxygen, this is hydrogen. Okay, there are two lone pairs. So the bonding angle is 104.5, or we are assuming 105 degrees. This source of degrees. So you see there is a sort of a polarity. So pure water has what? Slight electrical conductivity. So it can ionized. How does it ionized? H plus and OH minus ions. H2O molecule can be ionized simply in this manner. In the previous example, I did not take water because it is not that important to show you, because we are ignoring, because why? This ionization take place into small extent. See the center here, reversible reaction. This reversible reaction take place into a small extent. Therefore we ignore that, right? Okay, then in practical, if a reaction has completed more than 99%, what do you call? The chemical equations have gone to the completion. If you react A with B, so what will happen? if it completed more than 99%, you call it the equation has gone for its completion. Right? Okay. Okay, look at this one. A reaction between hydrogen gas and iodine gas. So this is a container. I have the square represent a container. In the container I have insert hydrogen and iodine. I have few points. One is it's closed, right? I prefer without writing much words. Sometimes a simple diagrams gives you more explanations, more things for you to catch up. It's easy to keep the things in your mind. That's why I drew this. So therefore you have to understand by seeing this square. It's a closed container and you need the temperature 573 Kelvin, right? Included the gases, right? If this process 90% reacted, I mean hydrogen and iodine reacted up to 90% and 10% remaining unreacted, what will happen? Yes. Now just keep this in your mind. What will happen? We took a container, closed container, and we gave the temperature, and this is though you kept for a long time, this won't proceed. Why? Because it reacted up to 90% and 10 is remaining, and though you kept it for a long time, I am repeating once again, though you kept it for a long time, this 10% won't start to react, right? Okay. See this one? This is the same container, the same method that you have used. I mean it is closed and you are using the same temperature, but you can see something. You have changed something. It is what? It is heat. So my dear children, here the difference between these two containers are the difference between these two containers is only heating, right? So in this case you will see partially decomposes. In the previous container, the container that you did not heat, completed up to 90%, sometimes 10% is remaining without go for completion. It actually depends, but I'm telling you a rough value, right? So when you give the heat, what will happen? It starts to decomposes partially. Fine. This is the equation for what we have discussed up to now. Gaseous hydrogen, 1 mole of gaseous hydrogen with 1 mole of gaseous iodine gives you 2 moles of gaseous hydrogen iodide. And my dear children, this is a reversible reaction, right? Okay. Then when there is no further change in the concentrations, we are not changing the concentrations, what will happen? Of the reactants and the products, the system is to begin, important word, you have come across with this word, but anyway it's important here, equilibrium. We are not changing the concentration of the reactants as well as the product. What will happen? The system has begin to its equilibrium. Let's see what is this. Okay, without a graph we are alone, right? So therefore look at the graph. I use time for x-axis and I use rate of reaction for y-axis. And I am going to represent dynamic equilibrium here. My dear children, I hope you can see, letters are a bit odd, I know that it's a bit hard to write here. You can see the blue curve. The blue curve shows you the backward reaction. Forward reaction, when it comes, we call it backward reaction. And when it when we draw what we call the green curve represent the forward reaction. But my dear, there's a time, even here we can consider, but here there's a time starts, there is no any changes. Both the concentrations of the products as well as the reactants comes to a certain stage. No more changes can be visible. So at that time you will call it equilibrium established. Right? Okay. Okay, look at the board. Conditions to be considered. Now we have come to the end of the lesson. Conditions to consider. According to this lesson, according to theory, there are conditions to be considered. First one, reaction must be reversible. What we discussed can be applied if the reaction is reversible. If not, you can't talk these conditions, or else our theory won't accept this. Second one, reaction must be in a, what is this? Closed container. You can't do the reactions in open container. You know the reason why. Whatever the product, whatever the reactants may escape. Right? So these two are important. Reactions must be reversible as well as reaction must be in a closed container. Right? Okay. Fine. Last point. Important features. What we have discussed, what our lesson explains is important features. The important features of this I have broke down into 3 steps. Number 1, both forward and backward reactions continuously occurring. What is it? Let me summarize it once again. One of the important features, I have broke the features into 3. The one feature is both forward and backward reactions continuously occurring. Right? Number 2, the rate forward, the forward rate should be equals to the rate backward. The rate forward should be equals to the rate backward. And the last one, the concentration of reactants and products remain constant. If you change the concentration of either what you call the reactants or the product, then we can't talk about this procedure. Our theory won't value for this. Right? I hope this is a easy part of the lesson, children. So please keep your note with you aside and the video. Then you have to compare the video and the the note and study more. Right? I know you all are clever. Please keep in touch. I wish you a good day. God bless you and bye.